Hi everyone, today I'm going to present a study on the architecture of graphic system with 3D acceleration support for abandoned operating systems. This research proposed a graphic system architecture suitable for microkernel operating systems, which can also be extended to other systems like Linux and QNX. A graphic system architecture suitable for microkernel operating system is proposed, which can be extended to other operating systems such as Linux and QNX. The main contribution of this study is the development of a graphics operating acceleration subsystem architecture that improve the performance of user applications. Let me begin by giving you an overview of today's presentations. We will cover the following sections. First, introduction, where we discuss the background and importance of the study. Second, research question and objectives, defining the key problem and goals addressed in the work. Third, graphic operation acceleration subsystem architecture, presenting the proposed solution and its components. Fourth, research and discussions, analyzing the outcomes and insights gained from our experience. Let's start with the introduction. Embedded systems are widely used in fields such as aviation, automobiles, and medical equipment, among which graphic information processing is a key component. For example, automotive dashboard displays, aircraft navigation system, and medical monitoring equipment all require efficient graphic processing capability. With the continuous growth of data and rendering complexity, embedded systems increasingly rely on hardware accelerators such as GPUs to reduce computation time and improve display performance. Traditional CPU-based graphics processing is not efficient enough to meet the demand of modern applications. Existing graphics processing systems have deficiencies in acceleration performance, such as complex memory management and limited GPU acceleration support. Some embedded systems rely on software rendering, which fails to fully realize the GPU potentials. The core question of this research is how to design an efficient graphics system architecture to support 3D graphics processing in embedding real-time operating systems. Our goal is to propose a solution that accommodates microkernel architecture, efficiently utilize the GPU, address memory management issues, and enhance stability and performance. The architecture consists of three layers: the user-level subsystems, the kernel-level subsystem, and the bottom-level subsystems. Each layer has specific responsibility, such as driver information storage at the user levels, memory management and interrupt processing at the kernel level, and display control and graphic acceleration operation at the bottom level. This slide presents the key components of the graphical operation acceleration subsystem architecture and their respective roles. 1. Text scheduler. Texts are assigned to priority queues, low, medium, and high. It confirms whether a text is executable based on its dependency. The timer is set to monitor text execution status. Once the GPU completes the test, it releases the associated resource. 2. Fast storage containers. Support 2 modes, single producer, single consumer, and multiple producer, multiple consumers. Atomic variables are used to ensure secure operation and access safety. 3. Synchronization barrier fence. These components create the destroy barriers. Check if they are completed and add callback operations. Reference counting ensure resources are released once they are no longer in use. 4. Reservation object. Assign share or exclusive access to memory resources. Wait for all relevant barriers to complete before proceeding with operations. 5. Interaction between layers. Two-way communications means the user layer sends a request to the underlying system, which processes the request and response. Synchronous interactions means every interaction waits for a response from the underlying system before continuing. These components work together to improve task execution efficiency, ensure resource safety, and enable seamless communication between the system layers. The tests were conducted using Baguette RTOS and Linux as the subjects. The hardware configuration includes a single-core MIPS processor and a display resolution of 1024 x 768. The GL Mark II benchmark tool was used to measure performance across various rendering scenarios. Baguette RTOS demonstrated significant performance advantage in some low-load tests, such as the build and texture scenarios, where its FPS was higher than Linux. This advantage can be contributed to Baguette RTOS optimized memory management and simplified system architecture. In this slide, we summarize the key advantages of Baguette RTOS based on our findings. In specific low-load scenarios, such as building and texture rendering tests, Baguette RTOS demonstrates a significantly higher frames per second performance compared to Linux. Baguette RTOS utilizes a 64 KB page size, which is notably larger than Linux 4 KB page size. This reduces the frequency of page translations handling by the CPU, leading to improved efficiency. By employing continuous physical memory as video memories, Baguette RTOS achieves faster memory access for specific types of graphics operations. This result highlights the system's efficiency in handling graphic operations under certain workloads, showcasing its advantage over traditional operating systems. Thanks for listening.